Shoot me an email. Right. I probably need to talk to Bree about it. Okay. Shoot me an email to remind me. It's morning, everybody. Y'all have a good weekend. Any questions on the homework before we get started? Anybody find the secret to getting on Hacker News? There should be some relationships.
None of the variables where you get predictors of the range. Where I could find. And no combination of them was good predictors.
I'd say one comment. That's kind of dope.
Like the number of comments?
Yeah.
Yeah, so I don't know that these are definitely causation, or yeah, probably not causations, but yeah, the more commented on stories tend to be higher ranked just because they've been on the front page, and so there's, you might find these kind of weird correlations there. Did anybody look up what the actual formula is based on?
Yeah.
What did you find?
The points and time.
Yeah, so it's like points over time squared or something like that.
Well, I think that some of the blog posts that I saw seemed to indicate that was the old way of doing it.
It's may have changed.
Just been updated since then, and now it's published and figured out.
Okay. I thought the website was open source, but it might not be. Anyway, okay, cool. Well, yeah. Is anybody surprised that predictors that we're looking at aren't, or the features we're looking at aren't, great predictors? Like, so title length or.
That wasn't surprising.
Yeah, that wasn't surprising. But like age and number of comments and points and stuff, I would expect some relationship there. Yeah.
If you have time, could you kind of go over, I guess, maybe do it for the R squared stuff? I'm trying to better understand.
Yeah.
Like the p-value being 0 is more significant versus if it's higher, it's less.
Like weighing those against, like how you look at the R squared, what holds more weight, get a picture.
So the R squared, basically, it tells you something. It's essentially like the percentage of the variance of the data that is explained by the model. So basically, if you graph your data points, right, they go up and down, right? If your model, the line that you fit, or the plane or whatever you fit, matches all that up and down, right, then this is going to be close to 1. Basically, you can think of this as a measure of like how tightly are the points, the data points to the line that you fit.
Oh, okay.
Right? So if this is close, if this is 1, that means every single data point is exactly on the model you fit. If it's 0, it means basically the points are scattered all over the place and there's like no relationship to your model. Right? The p-values, these are like a per coefficient thing, and these are probability that the coefficient you're looking at, the beta, equals 0. Okay. So if the beta equals 0, it means that that coefficient would be 0. So like if your title length coefficient was 0, it would mean that it has no impact on the model. Right? So let's say like there's no explanatory power for that.
So even if it's like p-value 0 with coefficient, for example, it says like 2.5, that coefficient is saying for every 1 unit, it would change 2.5. This is p-value 0.
So the p-value is 0. It means we are very confident that that coefficient is not 0. So that term is important. or that term has some predictive power.
Okay.
So if your p-values are high, it means there's a good chance that that coefficient truly is 0 and basically adds no value to the model.
Okay.
So
The coefficient is just how much it changes per 1 unit.
yes, so the coefficient is the beta that we're fitting. Yep. Yeah. So my kind of strategy for doing this, I throw all of my terms into the model, and I look at the p-values. I find if there's a p-value that's pretty big, I pull that term out. I look and see how the r-squared value changes. Okay. It will always either stay the same or go down. Okay. If it goes down just a little bit, then it's probably good. You've simplified our model, and it's about as predicted. Right? If it goes down by a lot, then maybe that term was important and you shouldn't have removed it. That's kind of my strategy for doing this. So the r-squared value, as you add more terms, so as you add more features that you're predicting with, the r-squared value can never go down. Any intuition for why that's the case?
It's not relevant, but you just end up with a coefficient of 0.
Yeah, so let's say I throw in the title length field. If it's not useful, the coefficient's 0, and I get the exact same predictions I had without it. So if it helps things, I'll have a non-zero coefficient. Cool. If it would hurt things, then I have a 0 coefficient, and then it's as if I didn't include it at all. So the r-squared value will pretty much always go down as you remove terms, but you're looking for the point where there's like a dramatic drop, and that's where you're underfitting. Okay. Any other questions?
The T statistics and kind of what role that's playing in interpreting it.
Where is that showing up in this?
I think just in the regression analysis, the T value for each.
And when you did logistic regression, or
Yeah.
just the column next to the p-value?
Yeah.
Okay, so that's where the p-value comes from.
Okay.
So just like when we did the hypothesis test, we computed like a z-score or whatever, so when we did the hypothesis test, if our hypothesis was true, the z-scores that we get from any particular sample would be distributed like this, and if we get a score way out here, we know that's really, really unlikely. That's exactly what's happening there. So the t-score is a test statistic, and if the coefficient were 0, we expect to get those in here, and that's where the p-value comes from. So this is like the shape we expect to get if the coefficient is 0. If I get something in here, the t-value is going to be high, the t-value is going to be close to 0, the p-value is going to be high. If I get something out here, it means my t-value is going to be really, really high, my p-value is going to be really, really low, so we can be confident that our coefficient is not 0. Basically, you don't really have to care about those t things. The p-value converts that into a more useful form. Did anybody try adding other predictors?
After class, I'm gonna try to add like a directory to the links.
Like the URL?
Articles, like the URL, to see if like the website are posted. And it's like there.
So you're thinking of doing that categorical, or? I think that might be a little bit tricky because there's so many different websites. Trying to think of like another way to group stuff.
Just
I mean, you could have a list of like hot websites or something that you put together and just have a yes or no. Yeah, another thing I think might be predictive is like, does it contain JavaScript or Tesla or Facebook or Google? My guess, or Apple. Seems like those would be useful features, but especially today. Yeah. Or maybe not. Maybe everybody's posting about Apple today, and so it's just only a couple of rise high, and everything else falls off. Who knows? All right, cool. So today we're going to talk about another technique for classification. So to draw a little picture today. So when we were doing logistic regression KNN, we were mostly in this quadrant here, right, where we were trying to predict a categorical value, the class of our data, based on mostly quantitative inputs. Okay. So for the logistic regression, we had to basically convert everything into a number so we could, plug it into a plane equation. For KNN, we have to be able to measure distances between points. So that generally, you could maybe work directly with categorical variables, but we just worked with normal Cartesian points, the normal distance definition. So today we're going to talk about what to do here, where our inputs have a lot of categorical. We have a lot of categorical features. We might have a mix of quantitative and categorical, but we'd like to deal with the categorical ones directly. And so today we're going to talk about decision trees. These are another pretty conceptually simple classification technique. You've probably all used one of these before. Maybe not for data analysis, but you've used the structure before. Building them is a little bit more complicated, and analyzing them kind of quantitatively is a little bit trickier, so we'll talk about that. But the idea of the decision tree is pretty simple. So these are actually kind of similar to KD trees in a way. We'll talk about that connection at the end, but I think they're a more familiar concept. So the idea is we model our data as a tree, or we model our classifier as a tree. The internal nodes are decisions. So we'll have one child for each branch of that decision. And then our leaf nodes will be predictions. Okay. So we might have so maybe we want to do like some predictions on voting based on some sort of demographic data. So maybe we know the age and level of education. So those are our inputs. Okay. So a decision tree I might come up with. So here, so maybe I have a decision node for the young voters. Okay. And how do we predict the young voters are going to vote? We'll say like, let's say we'll put the Sanders voters over here. Maybe we're doing some Democratic primary stuff here. So we'll say the young voters we predict are going to go for Sanders. And then maybe, so for everybody else, it's a mixed bag. So maybe here we do education. All right, so maybe we say if they have a graduate degree, maybe I think these are going to be Warren voters. Maybe here we have. Okay, so this is an example of decision tree. If I want to make a prediction, I just go down to the tree. I look at my the data point I'm trying to predict. I look at which branch I should take, and I just follow it down until I get to a prediction node. This is kind of like like the flow chart you see in the how to fix your I don't know, smart thermostat. It's like, is the power light on? Yes or no? Is it plugged into the wall? Yes or no? We just follow these branches until we get to a prediction. So these are they have some nice properties. So they work with categorical data in a really straightforward way. We don't have to use like git dummies or anything like that. We can just straight up use it, right? Because we just basically we have to put a Boolean function in each node. We could, I didn't do it here, but you can actually, these don't have to be binaries. So I could have an education node. I don't know which candidate goes there, but I could have a three-way split here, right? And it's just as easy to predict, right? The trees we're going to look at, I think, just because of ease of construction, are all going to be binary. But the structure works the same for any arity of tree, right? And I can mix and have binary and ternary and four-way nodes. It's no big deal. So these are also really easy to understand for a person, right? If you try to explain logistic regression to the layman, and talk about R-squareds and p-values and all that stuff, you're going to have a harder time, right? The decision tree, it's like, oh yeah, I get that. Like, I can look at this, I can interpret it immediately. Say, oh, young people like Bernie Sanders. Okay. So it's much easier to interpret these for humans and easier to understand, to give to a non-expert to use. So that's one advantage of this. A downside is they tend to not be as accurate as the other classification methods that we've talked about and we'll talk about. Okay. And I'll give you kind of a geometric reason for why that is a little bit later. Okay. Yeah, that's the key idea. Any questions about kind of what one of these looks like, or how you would go about using it? Yeah. So yeah, the leaf nodes are prediction nodes. The internal nodes are choice nodes. Okay. So if we want to use one of these, first we have to build one. Right? So given just a big old pile of data, somehow I have to construct a tree structure out of my data frame. Okay. Any thoughts about how we might do this? We would tree structure what kind of algorithm are we probably going to use? Recursive. So we're going to do a recursive algorithm. The algorithm that we're going to use is called the ID3, I think. Yeah, ID3. And it's pretty straightforward. If all of my data has the same class, what should I do? So I'm constructing this tree. All of the voters in the data that I'm looking at are Sanders voters. So what should I do?
Would you just stop here?
Yeah, so what kind of tree structure am I going to make here?
A leaf.
So if all of my data is the same class, then I make a leaf node. This is maybe unrealistic, so this might be most, right? So depending on how you construct these, you might have a threshold. So if I have 90% Sanders voters, then I'll go Sanders. Otherwise, another option, if I'm out of features, so I've been splitting, and I get all the way down to like really low level in the tree, and I've already looked at all of the different features of my data. So I've looked at age, I've looked at education, I've looked at income, whatever other fields I have. I have no more features to use. I can't make another choice node. So here I again just have to make a leaf node. So I might not have, the classes might not all be the same, but I can't make any more decisions. So I have to make a leaf node. And then the other case, so I have more features to use. There is some variation in the data that I'm working with. So I'm going to be vague about how you do this. But I'm going to, otherwise, I'm going to make an internal node with the best feature split. Okay. So I'm not going to tell you how I find it, but maybe I decide, for this data, I should split based on age with the cutoff of 35. And then I just do this recursively. Eventually, I will either run out of features or I will get homogeneous classes or homogeneous groups of data, and then I'll be at leaf nodes and I'll be done. So this is the general algorithm. There's two other things we might, two other kind of base cases we might put in here. Okay. So this is going to use basically all of my features until I get basically like perfect test accuracy. All right, I'm going to keep going down until my nodes are kind of perfect. I'm going to use all the data I have to do that. We'll see that really overfits data and tends to not be very good. So usually we also want to have either max depth and or a minimum node size. So either I'm going to say, I'm only going to go down 4 levels of my tree, or I might say if I only have 5 data points. I'm not going to do any more splits. I'm just going to make a leaf node with those 5 data points. Yeah.
So in practice with this example, I mean, would it basically be used like you plug in somebody's age and it would spit out like, oh, we think they'll probably go for this group?
So I would take a voter profile. So I would say, you know, this person has
Education.
this age, this education, whatever, and I want to predict how they're going to vote. So if I'm a political consultant, I'm going to do some polling. I'm going to make a decision tree like this. Then I'm going to look at the census data for whatever districts I care about and get the age, educational level, income, whatever for all the citizens, run them through my predictor, and see how many votes I expect to get. Right, so I know the features of my data, but I don't know how they're going to vote. Right, so I want to predict that based on the inputs. Cool. So does that idea kind of make sense? So we just construct these kind of top down. We split if we have to, and we can. Otherwise, we make leaf nodes for our prediction. If we want to find the best split, somehow we kind of have to describe, have to measure what best means. Okay? So how could we like measure how good a tree that we construct is? Like similarly sized?
Yeah, I mean, like, I guess in each layer, you'd expect it to subdivide half or you're holding to.
So yeah, one criterion you might look at is the balance of the tree. But that's not necessarily what we want, right? So if there are 0 Sanders voters above the age of 40, if we put all of them here, even if the tree is unbalanced, this is actually still the right thing to do. So the balance it might be important if we're thinking about like efficiency, but it's not necessarily a good goal. Like if we can isolate all of, figure out all the people in one group straight away, then there's no reason to like split them across just so that, we have even numbers of people. So balance might be less important here. Also because we're typically going to limit the depth anyway. So we don't really have to worry about like a tree that just goes on, an order n height tree. We're not going to have those problems here anyway. So the depth usually isn't such a huge concern for us. Do you want to comment?
Could you, I guess I'm thinking like almost like a cross-validation, but with your different decisions, like you could alter the amount of decisions you're going to use.
Like if you change the decision, how would it affect the...
Yeah, so look at, I guess, your accuracy afterwards if you're running.
Yeah.
Kind of like our last model. So
yeah, one thing you do is you just run the test or you run your training data through here and just see how many predictions you get right or wrong. And so that's a pretty straightforward thing. At some level, that's kind of the most important thing, right? Are your predictions good? Okay. So that's kind of the general idea. But there's kind of 2 slightly different ways of thinking about it that we use for decision trees. It's still basically accuracy, but it's kind of another way of thinking about it. Okay. And the idea is basically we want these leaf nodes to be one class, have be a huge majority one class, and not have very many data points from other classes. Okay. So if there is a bunch of Warren and Biden voters in here, then this isn't a great leaf, right? If there's 1 or 2 of them and 10,000 Sanders voters, then that's great. Okay. So there's 2 measures of this that we look at. One is called the Gini the Gini coefficient. The other is called the entropy. And these are both kind of similar, and they measure sort of the purity of the nodes. How much is like just one class versus mixed in with a bunch of others. So the Gini, basically, if this is close to 0, that means it's pure. Okay, so smaller Gini coefficients in your leaves means it means like the leaves are all going to be pretty accurate. Okay. And then the entropy also will be small. So we can look at the Gini coefficient or the entropy of our nodes. We can do this at the internal nodes too, and use that to kind of help us decide whether we are choosing good splits. Right? So my root node is going to have a pretty high Gini, right? Because all of my classes are all mixed together. After my first split, the Gini coefficient of my two children should be way smaller. Right? If I chose a good split, I'm going to reduce the Gini by a lot. Right? And so that's how we can kind of quantify how good we're doing with our splits. Right. Yeah.
Possible to have multiple leads that have the same outcome? Or is that
Yep. Yeah, you can. So especially if you have a binary classifier, so there's only 2 output classes, right? You're definitely going to have multiple leaves with the same value. So if we did like the college admission one, right, we'll have a bunch of branches that go to admitted. Well, for that data, probably we'll have a bunch of branches that go to not admitted, and maybe one that goes to admitted. But yeah, you can have duplicates at leaves. That's fine. So decision trees are pretty very easy to overfit. Okay? If I ignore the max depth or the min node size and just use all of my features until I run out or I get pure nodes at the bottom, I'm very likely to end up with really tall trees that get 100% training data accuracy, which sounds great, but is actually bad. Right? Because these are, we're making like binary discrete choices at each step, right? It's like it's really sensitive and kind of noisy. So overfitting is going to give me really bad accuracy with new data that I haven't seen before. Okay? So what we can either prevent it when we construct the tree by using the maximum depth or node size. We can also build a tall tree and then prune it. So we build our whole tree out, and then we take subtrees and like smush them into a single leaf node. And we'll also talk maybe later today if we have time, or tomorrow about 2 other techniques, 3 techniques that have fun names. Boosting and bagging are 2 of them, and then the third is random forests. So we'll talk about those 3, which are all techniques to kind of avoid overfitting. The first 2 are applicable more broadly. We'll talk about them for random forests, or for decision trees, and then random forests are kind of another technique. Okay. So yeah, we have to be really sensitive about overfitting. So geometrically, we can think about decision trees as basically like a KD tree. Very similar to a KD tree, right? We pick a dimension, right? So one of our features, and then we split on it, and it's an axis-aligned split, meaning we only look at one feature at a time. Right? So I'm only looking at age, or I'm only looking at education, or I'm only looking at income, or whatever else. Right? And so it's actually kind of like a discrete KD tree. That's the way of thinking about it. So geometrically, what we're doing, you can kind of think about, we're slicing our data into boxes. And then each one of these boxes is a leaf node. And so it's kind of like a geometric interpretation. It's probably not going to be a 2D thing. It's probably going to be like a 5 or 10D thing. So it'll be little hypercubes or whatever. But we're cutting stuff into boxes, and the cut lines, cut planes, are along sort of one feature at a time. Right? So it's kind of a geometric interpretation of what's going on here. It's the problems with the accuracy come from the fact that when we cut stuff up like this, we can't capture anything that's curved or like diagonal. Right? So if my real decision boundary, went something like this, I can't represent that very well with the decision tree because I can only have horizontal and vertical lines. Okay? So anything that depends on multiple, if I care about like age and income at the same time, like income divided by age or something like that, I can't capture that in my decision tree naturally. I'm going to generally have lower accuracy than some of the other methods because I'm limited in how I can kind of cut my space into regions. That kind of makes sense? Right. So we're very worried about overfitting. So it would be nice if we had a way to actually measure whether or not we're overfitting. Okay. So what were the techniques that we have talked about to detect overfitting our data? Do you remember what that was called? Cross-validation, right? So cross-validation is our tool for doing this. It works great if we have a ton of data. If we don't have so much data, then we don't really want to throw half of it away or whatever percent away to use as training, as testing data. Right? We'd like to use as much data as we can to train. One way we can kind of keep most of our data is something called k-fold cross-validation. I think I mentioned a couple weeks ago, but so the idea here is we split our data into k pieces. Okay, so if I have n voters in my data set, I'm going to have k groups of n divided by k voters. Okay, so maybe I split it into thirds or into fifths or whatever. Okay. And then I do this k times. For each one of these, groups, which we call folds, I train on all the other folds, so I leave this one out. Okay, so the first time I leave out the first chunk of my data, the next time I leave out the second chunk. And then I compute the error on the left out chunk. So, and then at the end, the total error or whatever is either the average or the max error over the folds. Okay. So I'm doing the train test data split. I'm doing it k times. So each chunk of my data will be the test half of my data one time, and will be in the training data k minus one times. And so I'm going to do my training and prediction k times. So this lets me kind of reuse my data a bunch of times so that I can have enough data to do training and testing. That kind of makes sense.
Keep it from overfitting.
So if I overfit, I am still doing a train test split, so I will probably detect it here when I compute the error on any one of the folds. Yeah. So if I overfit, I'm probably going to notice it here. Okay. Cool. Any other questions about kind of the general idea or the mechanics of the decision tree? All right, cool. Let's take a look at some code. If you want to follow along today, there's a couple of libraries you'll need to install. So one from Homebrew, one from Pip. They should be pretty fast to install. So GraphViz is a library that takes like a text description of a graph. So it's like kind of like an HTML for graphs kind of language, and draws it. So we're going to be drawing these decision trees, so we need that for it. And then Py.Plus is just like a Python library for interacting with it. Cool. So the first data set we'll look at is data set of who survived on the Titanic. So we have a lot of information about all the passengers. So we have whether they survived, their class, right? So are they in first class or were they in steerage? Name, the Hacker News stuff. I would be curious to see if like the length of the name is predictive of whether or not you survived. Who knows? We have the sex, we have the age, the number of siblings and spouses aboard, number of parents or children aboard, ticket number, which I don't know why that would be useful, but fare, cabin. The embarked is, so I guess the Titanic actually didn't just go from A to B, it like stopped and picked up people in a few different spots in England before it went across, so that's what that's about. So this is the data that we have about, and we want to try to predict like who would survive, or the likelihood that you would survive based on some characteristics about you. Cool. So we could very easily, I think we have enough features. Well, yeah, it would be pretty easy to come up with a decision tree that predicts every single passenger 100% accurately, but it would be super tall and it wouldn't really tell us much. Right? And we would definitely be overfitting the data if we did that. So we're gonna try to come up with a model that actually gives us some insight into what caused people to live or die. Anybody have any guesses on what the important features of important predictors for whether you live or die would be? You think class, sex, yep, women and children first. So we expect that the sex and the class probably are going to be pretty important, but who knows? You have to look at the data. Yep. So yeah, this is a decision tree that was. This looks like it's generated. I don't know. This is not from the tool that we used, but this is what a decision tree looks like, right? And it looks like 36% of women survived, or sorry, maybe 75% of women survived, and there were 36% of the passengers, and most of the men died. So, unfortunate. So, so adult men seem to die at a pretty high rate. Cool. So this is how we build them, right? We start, if we have all the same data, we make a leaf. If we run into attributes, we can't make any more decisions, we make a leaf. Otherwise, we split as best we can, and then we either hit the normal base cases or we stop because of the maximum depth or minimum node size. Basically, to come up with the best split, we look at a bunch of possible splits and then choose the best by looking at the error loop. So, so this is our data set. So we got the Titanic data set. Yeah, this is what the data looks like. Going to do a little bit of cleanup. So this fill_NA function says any entry that's NaN, so like missing data probably, we're going to fill that with just the mean age. I don't know. Curious to see how many NaNs there actually are, but and then we're going to change the sex to a numeric score. I don't think we really need to do that here, but we'll. And then we'll change the embarks to numeric again. I don't think we really need to do that. But. And then these are the features we'll look at. So we're interested in whether or not they survived, and we'll look at the class on the boat, sex, age, number of family members, how much they paid, where they left from. So we're throwing away like the name, the cabin, some other stuff. So we describe the data. So it looks like there's about 900 passengers that we have data for. I have no idea if that's how big of a sample of the boat that is. Does anybody know how many people are on the Titanic? Yeah, it seems small to me. So it looks like we have about half. 1,500 people died, so. Okay, so I guess, so this is, so I guess we, we don't have all of the data, so maybe we want to predict about the other people that we don't know for sure here or something. But, so we have 900 people. Looks like about 40% survived, which is higher than I was expecting. Mostly lower class. Mostly men, I think. The women are 1. So about 65% men, 35% women. Pretty, he was kind of young. With the median age of 30. Okay, maybe not that young. Most people had half of a family member. So the next thing we'll look at for doing just a little bit of exploratory analysis is just a pair plot. So we'll kind of see like what correlations there are between the various things. So this is like the matplotlib scatter matrix. The Seaborn pair plot just is a prettier version. So not easy to see. Is there anything in here that kind of jumps out at people? So this is hard to make much of anything versus survive because we just have the dots. Yeah, so I don't see much here that tells us anything all that interesting. I guess most people got on at the last stop, I guess. Yeah, so again, nothing obvious here that's going to help us with our predictions, so we'll throw it into just try to train a decision tree on it and see maybe that'll tell us something. So we'll look at, we just want to see did people survive or not. And so we're going to look at different groups of features. So we're going to, this function is going to take the features that we care about, extract only those columns, and then we'll split into a training and testing set. And then here is code to draw the decision trees that we come up with. So this is using the PyDot+ library. So this is using GraphViz to draw the stuff and make an image from it and then draw it. So let's look at, we'll make a decision tree that only classifies based on the sex of the passenger. So this is the only feature we're including, so we're just going to have that one column. We're going to make a decision tree with our training data, and then predict. Sorry, we're going to fit our decision tree, predict on get our training accuracy score and our testing accuracy score, and see how we do. So on our training data, we get 81% accuracy. On our testing data, 75. So it doesn't really seem like we're overfitting here because if you look at the tree, we really could not possibly be overfitting. Right? We have one binary decision that we could make, and we're making it. So this is what our decision tree looks like. So we look at the Gini. So this tells us basically how mixed up the survivors and non-survivors are. So here it's relatively high. here it's much lower, here it's a bit lower. So basically the women had a tended to survive. Wait. Sorry, the women tended to survive over here. So here it looks like 115 survived, 41 died. For the men, they mostly died. Okay. And it looks, if we look at the Gini, we can see that here this node is more pure, meaning there's a fewer percentage, a smaller percentage of men survived than women died. If that makes sense. So for a one node decision tree, like it was a pretty good classifier. This gives us 75% accuracy. Not a bad model for being basically the simplest one you could do. So we add some more features. Let's say we look at the number of siblings and spouses, and then do the same dance. Here we increased our accuracy on the training data, and it looks like we slightly decreased the accuracy on the test data. So we went down about 0.2% and went up just a little bit here. So the split between the training and testing data went up. So that's a good indicator that maybe we're overfitting. And our decision tree is much more complicated, right? So we're splitting on sex first, and then we have like a whole bunch of different splits based on siblings and spouses. Again, we can get pretty low Gini coefficients here, but this is much harder to interpret, right? So it looks like if you were a man that had a lot of siblings and spouses on board, you're going to die. Or wait, sorry. If you're a man, probably you're like a single man, you're going to die. If you had maybe a wife or a brother on board, then probably still going to die, but less likely. Right? So, you know, we can improve our test accuracy, but I don't know that this really doesn't really add much to the model. Not explainable. Okay.
Question?
Yep.
So is Gini value the lower the boundary?
So a 0 of Gini means that everything is the same class. So this one is a Gini of 0, meaning every single person in this node died. And so for prediction, that's probably means better, because we're going to get a higher training accuracy score.
So value equals to 11, 0 means 0 out of 11 survive.
So this is like it's like a ratio of how mixed up this node is. So here, like, it's a Gini of 0.45, and we had a mix of both survivors and deceased. So the Gini actually is it comes from an economist, and it's actually originally used to measure like income inequality. It gives you a number of like how even the distribution of wealth is in the population. So that's where it comes from. Okay, so looks like by adding the spouses and siblings, we slightly increased our training accuracy, but probably overfit our data. Now let's just throw everything in here. So we're just going to put all of our features in. We get 98% training accuracy. Pretty good. 76% test data. So that is about the same as it was. Right? The gap has gotten even wider. So again, we're probably in that overfitting zone. So this is what our tree looks like. all of our bottom nodes are pretty dark, which means they have really low Gini coefficients. So that's, I mean, so all of our leaf nodes are very pure. If you were to zoom in, you'd see that there's like hardly anybody in any of these. So this one, I have one sample here, one sample here, one sample, one sample, one sample, one sample. So really, I'm giving each person their own leaf node. So probably it doesn't generalize very well. And it's totally uninterpretable. The interesting thing is that, so if we look at what the splits were, it's a little bit interesting. So for we still have men and women are still the best split. For the men, it looks like age is the next best predictor. And for the women, it's the class. So the first class ladies seem to survive at a higher rate than the poors. So, that's but probably the rest of the stuff is not helping much with that, with understanding or prediction. Okay. So we're going to throw in these limits. Okay. So we'll have a max depth for our tree, and we'll have a minimum number sample split. So we're not going to split two passengers into their own nodes. Okay. So we'll just start with a max depth of 3. And you can see this is our old tree. This one's much easier to interpret. And again, so now we have the same splits at the top with still splitting on sex, age, and class. We still have pretty high or pretty low Gini coefficients for most of these. Not all of them, right? So looks like splitting based on where people came from didn't add a lot of predictive value. Right? Also, wow, these are really, really young passengers. So yeah, this probably also wasn't that great that we devoted a whole node to one very young child. But we're overfitting less, right? So our testing accuracy went up a little bit, which is good, and so the gap is not quite so bad. Okay. But we still have a split of, really small sample size, or really small nodes being split. So probably still not great. So how about instead we look at the minimum number of samples to split. This is, let's see, slightly higher on the training, almost slightly worse on the testing. So this one seems to have overfit slightly more. From looking at it, I doubt anybody is surprised. Right? Again, this is not really comprehensible. So probably not a great model. So if we add both of these together, so max depth of 3 and a minimum split size of 10, this looks exactly like I think this might be exactly the same as what we got here. Looks like the min split size did not have much of an impact. Yeah. So in this case, the minimum split size didn't make any difference. Let's add another level here and see what we get. Still about the same, so I guess probably the simpler model of depth 3 is probably better. So yeah, we're getting about 80% test accuracy with models that are, comprehensible. And so if we go back to the simpler model, so yeah, it looks like if you're a man, you you're going to survive if you're really young, or maybe if you're like first class. Otherwise, you're probably going to die. If you are a woman and you are first class, you're probably going to survive. Otherwise, it looks like about 50-50. So that type of explanation probably you couldn't get from any of the other methods that we talked about, right? Trying to understand like all of the different coefficients for logistic regression. They're not really that obvious. And the relationships between them are kind of tricky. For KNN, there's not really, you can predict, but there's no really generalization about what it means, right? So this gives us nice explanatory power. They're nice and easy to explain and interpret. We can draw them. We don't need dummy variables, right? They deal with categorical data directly. But they tend to be lower accuracy, and they are very easy to overfit and very sensitive to the data. Yeah, any other questions about decision trees? Yeah.
So there's multiple decisions that lead to perished or survived. Why does that exist? So what, we have one parent that leads to two leaves that are both perished, for instance.
Yeah. So why do this? If we are just doing classification, it doesn't add anything. But if we interpret the like percentages here, it's pretty useful information, right? So, right, knowing that you are more likely to survive if you are in first class is like useful to know. If I'm just doing predictions, yeah, I would predict both die, but it is extra information that helps with interpretability. Another thing you could do is you could do like probabilistic predictions. So if I'm down here, I pick a random number to decide if they live or die based on the percentage, based on the probability. So that's another use. Other questions? Okay. So we have some more time. So we'll start talking about the other techniques for avoiding overfitting. So the first technique we're going to talk about is related to basically understanding how sensitive our training is to our data. So we have some data, we do some fit, right? We might be interested to know, like, okay, if I went out and I repeated the same experiment, got new data, and did another fit, how similar would the model that I fit be to the one that I just computed, right? So we looked at this example when we were looking at linear regression, where we made a whole bunch of data sets and we fit a line to each one, and then we saw that the lines were kind of all pretty close to each other with slight adjustments up and down and different angles. Everybody remember that? Okay. In that case, we collected like 1,000 data sets to do that, which is usually not a feasible thing to do. Right? If you're like a pollster and you want to, learn something, understand your models, you can't go do 1,000 more polls to like figure that out. Right? If you're doing some sort of experiment, like the LHC is not going to let you run your experiment 1,000 times just so that you can, feel confident about the sensitivity of your models. So we're going to look at a technique for letting us do that kind of analysis without actually having to rerun the experiment. And so the technique is called bootstrapping. And what we're going to do here is basically we're going to generate new data sets. Okay? And we're going to do it in a way that sounds really dumb, but actually works really well. So we're going to generate a new data set. By sampling with replacement. Okay. So let's say I have 100 data points. I'm going to generate a new data set of 100 data points by just picking 100 random samples out of my data that I've collected, and I could pick the same sample multiple times. Okay. That's all we do. So we just sample with replacement to get a new data set, and then we can do our training or whatever on that, and that allows us to train multiple models on different data that we kind of assume is representative of the data that we're interested in. And then so we can get an idea of how sensitive our model is. So that's the key idea of bootstrapping. Okay. So if we do that, right? So maybe I do this. So let's say I'm doing like a linear regression. Maybe I make like 100 data sets from my original data. And I fit just do a least squares regression on each one. And now I can look at the mean and the variance of my betas. So if my variance is high, then it seems that my model is very sensitive to my data. Or if my variance is low, then that means it's pretty it's not that sensitive. And if there's noise, then I shouldn't expect it to change my results for a while. So this kind of seems like a ridiculous idea, right? But it actually works pretty well in practice. Yeah, it can give us an idea of kind of the variation we would expect in our models if we took a whole bunch of samples of data. Yeah.
So how do I make 100 data sets from original data?
So to make a new data set, all I do is I just pick however many samples I want in my new data set from the original, but I allow myself to pick the same one multiple times.
Then they are just similar, the same data.
It is. They all come from the same data. Yeah, it is. It sounds kind of dumb, but the assumption is that if the data that I have is representative of the real population, then this is going to give me this is going to give me something similar to what I would get if I sampled the population directly.
But then I guess it would just give a very high weight on that data that you keep picking up, so it would just somehow smooth
Yes, so, yes, I am gonna reuse the data I collected a bunch of times. If, assuming that it is representative of the real data, then it will work out okay. Yeah.
Seems like you'd be pretty confident, or it'd be hard to be confident that it's representative.
Yeah.
You're just doing that based off the p-value prior.
Yeah, I guess I don't have a good answer for what should make you confident that it's representative. The larger your original sample is, the more confident you can be. So you probably wouldn't want to do this with 5 data points. But if you had 100, then you know you'd think you have a reasonable sample.
Yes, maybe I missed it earlier, but your sizing, are you trying to replicate the same size as your original data set or choose a different?
That's a good question. It probably depends on exactly what analysis you're doing. If you're fitting a whole bunch of models, probably you would use a smaller subset. So if I have, so maybe I use like half, I generate new data sets that are half as big, so my training is faster. Yeah, I don't have a great answer for that. So this allows us to get some idea for, you know, how much the range of possible, sort of the range of model parameters that are probably reasonable for the population. Right? If I do a logistic regression, if I use this for logistic regression, right, I'm going to get a bunch of little S-curves that are all shaped slightly differently, right? And if I look at the variation between all those parameters, I can kind of get a sense for like, okay, like there's kind of this range of sort of uncertainty that I expect to be about this big, and then as I get away from that, you know, this is where I can be pretty confident about my predictions. So that's bootstrapping. Right? Again, sounds dumb, but works pretty well in practice. If I were, if you were to use bootstrapping to get a new data set of the same size, just based on the probability, you get about 2/3 unique data points, and then the last third would be duplicates of the original third is kind of what you expect. So you're kind of using like, you know, 2/3 of your data each time, but the n that you get is the full size. Right. So that's bootstrapping. Right. It's not going to reduce the variance directly, but it's a way to kind of understand the sensitivity of your models to the data. Questions about that? All right. And then the last thing we'll talk about today is bagging, which is specific to decision trees. And the idea there is because the decision trees are really sensitive to the data, we want to kind of try to smooth out that sensitivity. And so the idea there is we bootstrap a bunch of data sets. Okay. We train a decision tree on each one. Okay. And to do prediction, we run our input through all the decision trees and have them vote on the final class. Okay. So to predict, we predict on all the decision trees So this is a way to kind of to try to smooth out the really high variability of the decision trees, the really high sensitivity, by making a bunch of kind of similar decision trees, and then using voting to try to get something a little bit sort of smoother at the end. That kind of makes sense. It seems kind of like a reasonable thing to do, right? We're kind of, one way of thinking about it is like we're training on a subset of the data, and we're going to get slightly different splits, right? And then we kind of average them out at the end by voting. So that's kind of the idea. Yeah.
So isn't part kind of meant to reduce like the chance that you just pick like a bad subset or make some decision tree?
Yeah, I would say it's more to, so the way that we construct these is we find the best split, right? And then we split based on that, and that's like a big choice. If the one we picked was like barely the best, right, we might get a totally different tree that might work better if we had chosen something else. And so by shuffling the data a little bit, we're going to make different choices as we go. And so we have a bunch of things that might be overfitting, but when we kind of average them out, we will have reduced that overfitting. Yeah. It's hard to overfit when you average a bunch of stuff together.
So it's kind of like anti-aliasing.
Yeah, that's a good way to think about it. All right, so we're making these like big, impactful binary choices that you could go, multiple ways. And by doing this bootstrapping, we're kind of trying to get it to go multiple ways, and then averaging things out at the end. Cool. So I think we'll end there. We'll talk about random forests tomorrow, which is just similar but slightly different idea. And we'll also start talking about support vector machines. How many people have heard of SVMs? They're like it's a weird name. It's a pretty cool concept. It's a super powerful classification technique. Yeah, they're pretty awesome. So we'll take a look at SVMs. Right. See you all tomorrow. Thursday I'm gonna be out of town, so you'll have one of Varun's makeup days. So be prepared for that.